Seismic waves, unraveling the rumbles. Seismic waves, unraveling the rumbles. Introduction. The Earth is a dynamic and ever-changing planet, constantly in motion beneath our feet. While most of these movements go unnoticed, occasionally our world reminds us of its power with forceful tremor. And earthquakes. These seismic events are the result of seismic waves, which travel through the Earth, unraveling the rumbles and providing scientists with valuable information about our planet's surface. Understanding seismic waves. Seismic waves are vibrations that travel through the Earth following an earthquake or other geological activities. These waves are initiated by the sudden release of energy accumulated within the Earth's crust, causing the ground to shake. Seismic waves can vary in magnitude and intensity, resulting in varying degrees of impact on the surface. Types of seismic waves. 1. Primary waves, P waves. P waves, also known as primary waves or compression waves, are the fastest and least destructive seismic waves. They travel through the Earth by compressing and expanding the material they encounter. Similar to sound waves, P waves can move through solids, liquids, and gases, making them the first wave to reach seismographs located far from the epicenter of an earthquake. Their speed allows for an early warning system, providing precious seconds or even minutes to alert people of an impending earthquake. 2. Secondary waves, S waves. S waves, also called secondary waves or shear waves, follow P waves but arrive later at seismographs. These waves propagate by moving the particles of the Earth perpendicular to the direction of wave travel. Unlike P waves, S waves cannot pass through liquids, thus indicating whether the Earth's interior is fluid or solid. S waves are more destructive than P waves, causing the most damage during an earthquake. 3. Surface waves. Surface waves are slower than both P waves and S waves but are responsible for most of the damage caused by earthquakes. They travel along the Earth's surface and result from the interaction of P wave, S and S waves with the surface. Surface waves can be classified into two main types, love waves and Rayleigh waves. Love waves move in a horizontal, side-to-side motion, similar to a snake crawling on the ground, causing damage to structures. Rayleigh waves, on the other hand, create an elliptical rolling motion, similar to ocean waves, resulting in ground shaking and surface displacements. Characteristics of seismic waves. Seismic waves possess unique characteristics that help scientists to identify and analyze them. The key characteristics include 1. Frequency and period. Seismic waves have a frequency, which refers to the number of waves passing a fixed point in a given amount of time. It is measured in Hertz, Hc, and determines the pitch or tone of a wave. The period d, which is the reciprocal of frequency, refers to the amount of time taken to complete one full wave cycle. 2. Amplitude. Amplitude describes the maximum displacement of a wave from its resting position. In the context of seismic waves, it reflects the energy released by an earthquake and can be used to estimate its magnitude. Stronger earthquakes produce larger amplitudes. 3. Velocity. Velocity relates to the speed at which seismic waves travel through the Earth. The velocities of P waves, S waves, and surface waves differ due to variations in the density and stiffness of different materials encountered along their path. By measuring the arrival times of P waves and S waves at multiple seismographs, scientists can calculate the distance to the earthquake's epicenter. Applications of seismic waves. Seismic waves have numerous applications, providing scientists with valuable information about the Earth's interior and enabling the prediction of earthquakes. Some significant applications include: 1. Seismic tomography. Seismic tomography is a technique used to create images of the Earth's subsurface by interpreting how seismic waves propagate through different materials. By analyzing the variations in travel times and velocities, scientists can map the distribution of various rocks, minerals, and fluids deep within the Earth. This knowledge is essential for understanding the structure of the Earth, including heat presence of subduction zones, faults, and mantle plumes. 2. Earthquake early warning systems. As mentioned earlier, P waves are the fastest seismic waves and can travel ahead of the more damaging S waves and surface waves during an earthquake. By detecting P waves and determining their arrival time, it is possible to issue an early warning, providing vital seconds or minutes for people to seek safe shelter. These warning systems can help reduce casualties and damage during seismic events. 3. Estimating earthquake magnitude. The amplitude of seismic waves is used to estimate the magnitude of an earthquake. Magnitude is a measure of the energy released at the earthquake's source. By analyzing the amplitude recorded at var I seismographs, scientists can calculate the earthquake's magnitude using established formulas. This information is crucial in assessing the potential impact of an earthquake and preparing for subsequent events or aftershocks. Seismic waves, the vibrations that travel through the Earth following an earthquake or other geological activities, are a crucial aspect of understanding our planet's interior. These waves can be categorized into three main types: primary waves, secondary waves, and surface waves. Primary waves, also known as P waves, are the fastest and least destructive seismic waves. They can travel through solids, liquids, and gases, which allows them to provide an early warning system for earthquakes. Secondary waves, or S waves, follow P waves and are responsible for more damage during an earthquake. Unlike P waves, S waves cannot pass through liquids, providing information about the physical state of the Earth's interior. Surface waves are slower than both P waves and S waves but are responsible for most of the damage caused by earthquakes. Seismic waves possess specific characteristics that help scientists identify and analyze them. These characteristics include frequency, period, amplitude, and velocity. Frequency refers to the number of waves passing a fixed point in a given amount of time, while period refers to the time taken to complete one wave cycle. Amplitude reflects the energy released by an earthquake and can be used to estimate its magnitude. Velocity relates to the speed at which seismic waves travel through the Earth and varies depending on the materials they encounter. The applications of seismic waves are vast, contributing to our understanding of the Earth's interior and aiding in earthquake prediction. Seismic tomography is a technique that uses seismic waves to create images of the Earth's subsurface, providing valuable information about the structure and composition of our planet. Earthquake early warning systems utilize the faster P waves to issue warning Gs before the arrival of more damaging waves, reducing casualties and damage. Seismic waves amplitude is also used to estimate the magnitude of an earthquake, providing crucial information for assessing potential impacts and preparing for subsequent aftershocks. Seismic waves are fascinating and crucial for understanding the Earth's interior and predicting earthquakes. They come in different types, including primary waves, secondary waves, and surface waves.